An action potential is the neuron's way of transporting an electrical signal from one neuron to the next. This is a picture of a neuron where you have the dendrites in one end and the axon terminal in the other end. In the middle of the neuron you will find the axon. This is where the electrical signal travels from the dendrite to the axon terminal. This is a picture of a myelinated neuron, which is covered with a myelin sheath, which allows the electrical signal to travel faster down the axon. So instead of activating every ion channel down the axon, only the channels in the spaces between the myelin sheath, called the node of Ranvier, is activated and generates an action potential. So let's take a closer look at the axon. On the membrane of the neuron you will find ion channels that are closed when the cell is in its resting state. The neuron is able to create an action potential because of the concentration difference of ions between the intracellular space and the extracellular space. There is a higher concentration of sodium ions outside the neuron and a higher concentration of potassium ions inside. The extracellular space is more positive than inside the neuron. This creates a voltage difference of minus 70 mV, which is created by leaky ion channels that are more permeable to potassium ions than sodium ions, which causes potassium to leave the cell and only a small amount of sodium ions to enter. The sodium-potassium pump also regulates the environment by pumping out 3 sodium ions in exchange for 2 potassium ions. The minus 70 mV is the neuron's resting potential, but when a neuron is stimulated by a presynaptic neuron, it causes sodium channels to open, letting in positive ions. This will change the electrical environment and make it more positive inside the neuron and less positive outside. This is called depolarization, and which causes a chain reaction where the next sodium channels will open, letting in positive ions all the way down the axon. Shortly after the channels have opened, they will close again, and potassium channels will then open, letting out positive potassium ions to recreate the negative environment inside the neuron and the positive environment outside. This happens at around plus 40 mV and causes a repolarization where the intracellular space becomes negative again. The neuron then reaches a state of hyperpolarization where the cell has let out too many ions and has now become more negative than the cell's resting potential. This is quickly corrected by leaky ion channels and the sodium-potassium pump, and the neuron then stabilizes at the resting potential at minus 70 mV. The action potential that has traveled down the axon reaches the axon terminal where vesicles with neurotransmitters are released out into the synaptic cleft where the electrical signal will stimulate the next neuron.